equal area criteria. We developed already a string equation. When there is an imbalance occurs in the system, the load angle is swinging, then that swinging is described in the form of a string equation, that is md square delta by dt square is equal to Pa. That is, string equation we know is the nonlinear in nature. The formal solution of such equations cannot be explicitly found. Therefore, it is very difficult to get a solution of a single machine connected to infinite bus, and you have to go for a digital computer methods are normally used to find the solution for string equation. To examine the stability of even two machine system without solving the string equation, a direct approach is possible. That is what we are calling as equal area criterion. Here we are using the principle of equality of areas called equal area criterion. To determine the stability of the system under a tangent condition, without solving the string equation, it is possible for us to decide whether the system is stable or not. That is, we are using that is a criteria, that is equal area criterion. Equal area criteria method, which is applied to the machine swinging with a infinite bus, we'll study here. We know that the string equation, it is given by md square delta by dt square, that is equal to Pa. That is, for deciding the stability or unstable condition of the system depending upon the nature of change of angle delta. That is, if the system is unstable, in that case, the delta, that is a load angle or a torque angle, continue to increase indefinitely. That is, as the time elapses, if the angle delta goes on increasing, then that is called as the system is unstable. That is, if the delta is increasing indefinitely with the time and the machine loses synchronism. In other words, in other hand, if the system is stable, when it is a system is stable, that is when delta performs some oscillation initially, then settle down to a new value of angle delta. In that case, we are calling the system is stable. That is, if the system is stable, if delta performs oscillation, it is not sinusoidal in the nature, whose amplitude decreases in actual because of damping terms. That is, because of there is a imbalance, there is swinging of the delta, that swinging of the delta, that is oscillation, which is counterbalanced by the damping in the system. Then ultimately, if the damping are sufficient in the system so that they are suppress the oscillation of the delta, and ultimately the delta is settled down to a new value, then the system is become stable. That is, we are deciding the stability of the system based on the variation of the delta. You can see here because of the imbalance between the input and output, then there is a initially there is a oscillation which is not sinusoidal in the nature, then it is settling down to a new value here, the delta. Here the delta stop changing, therefore the system is stable, or in other words, the rate of change of the delta becomes 0 after some time, then the system is stable. That is why what I am putting here is d delta by dt is equal to 0, therefore the system is stable. If the angle delta goes on increasing with respect to time, see here, that is the angle delta goes on increasing. It is not making any oscillation and it is settling down to new value. It goes on increasing, then the system is unstable. The system is unstable. Okay. Then the stability of the system can be decided by the variation of the delta with respect to the time. Now once again I am considering here a swing equation, that is md square delta by dt square, that is equal to pa, that is the accelerating power. We know that the accelerating power, which is written for a generator, it is a difference between the mechanical input which is greater than the electrical output, therefore there is a acceleration. Therefore the single equation is md square delta by dt square, that is equal to pa. Just what I am doing here is I am multiplying both sides, that we have discussed already this issue of making the finding out the integration of the swing equation. Just what I am doing here is I am multiplying both sides to d delta by dt and integrating with respect to time t. That is, I am multiplying md delta by dt on either side of this equation and integrating with respect to the time t. You can see here, that is just I am multiplying here 2 d delta by dt to this equation on both sides. Okay, then I am integrating with respect to dt here. Okay, now the solution of this 2m d square delta by dt square d delta by dt, in the last session we seen that the integration of this is equal to, it is d delta by dt whole square. That is what I am getting here is, it is m, that is 2d square delta by dt square d delta by dt with respect to dt. The integration of this term, what I am getting is d delta by dt whole square. The m is constant as it is given here. That is, in other words, the differentiation of d delta by dt whole square, that what I am getting is 2d square delta by dt square into d delta by dt. Therefore, the integration of this is d delta by dt whole square. That is what I am getting is this solution, that is integration of the left hand part. And in the right hand part I am keeping as it is 2 I am taking outside, which is a constant. It is integration because of there is a change in the input and output, therefore angle delta has to be changed from one value to another value. Therefore I am taking the integration between the limit delta naught to delta. Because of the change in the input and output, the angle delta has to adjust itself, so that I am taking delta naught to delta, it is ps minus p, that is ps minus p d delta, because dt get cancelled, it is now ultimately it is integration in the right hand side with respect to d delta. Okay. Now, what I am interested is d delta by dt. Therefore, what I am doing here is I am taking the square root of this, so that what I am getting is d delta by dt. The m I am transferring to other side. Therefore, it is 2 by m integration between delta naught to delta, ps minus pe d delta raised to 1 by 2, because I am taking the square root on both sides. The ps minus p d delta is nothing but your pa d delta. Already it is defined here. Pa is equal to ps minus p. Therefore, it is delta naught to delta pa d delta. Now, we are defined the stability of the system when d delta by dt is equal to 0. In that case, the system is 0. Therefore, for the system to be stable, in that case, d delta by dt is equal to 0. If d delta by dt is equal to 0, then this term is also, that is 2m integration between the limit delta naught to delta raised to 1 by 2 is also tends to 0. That is same thing I am writing here. If d delta by dt is equal to 0 for the stability, in that case this term is also equal to 0. That is 2m by delta naught delta pa d delta raised to 1 by 2 is also equal to 0. This is 0 only when, that is 2 by m is the constant, it cannot be 0. Therefore, it is integration between the delta naught delta pa d delta, that must be equal to 0. Ultimately, if d delta by dt is equal to 0, means what do you mean by that is the accelerating power is equal to 0. After some time, the accelerating power is equal to 0. What do you mean by the accelerating power is 0? In the event of any imbalance in the system, there is a process of both accelerating and decelerating, because of there is swinging of the delta. Sometimes there is a acceleration, sometimes there is a deceleration. Ultimately, there is the damping torque, which is counteracting the swinging of the delta. Ultimately, it is settled down to an value. Here there is accelerating area as well as the decelerating area. If both areas are equal, then the system is stable. Ultimately, at the end of the settled down to a new value, if the accelerating power is equal to 0, then the system is stable. Therefore, the condition for stability can therefore be stated as the system is stable if the area under accelerating power delta curve reduces to 0 at some value of delta. That is, the area under accelerating power, if it is becomes 0, then the system is stable. In other words, the positive accelerating area under PA delta curve must be equal to the negative decelerating area, and hence the name equal area criteria. I told you there are two processes there, the occurring accelerating and decelerating before settling down to new value. In that case, if the decelerating area and the accelerating are equal and opposite, then the system is stable. Ultimately, the total accelerating power becomes power is Pa is equal to 0. That is demonstrated here. This is what I am showing is, it is a part of the PE, that is a power delivered. Then initially the machine is operating at this particular point, here both the mechanical input as well as the electrical output are equal at this point. Both electrical power output and the mechanical power input both are equal, PS and P are equal. Therefore, it is operating at stable condition at this point. Suddenly I am increased the mechanical power input to the machine. From here to here I am increased. Previously this is the value of PS. Now suddenly the PS is increased. However, the PS is greater than the P. PS is greater than P. Okay. Then what happens? Then the load angle delta has to change, so that it has to settle down, because there is an imbalance between PS and P. Therefore, the angle delta goes on changing here. At this particular point, both mechanical power input and electrical power output are the same. But delta is not settling down to this value because of the inertia. It goes on increasing, and when it reaches to a particular synchronous speed, then it stops changing. Initially, when there is a disturbance occurs, when the mechanical power input is more than the electrical power output, there is a maximum swing from delta naught to this value. That is what I am calling as the value delta. Then it is swinging between these 2 points. It goes on damping, it goes on decreasing, and ultimately it is settled down to this value. Here you have got the 2 areas. It is the accelerating area and the decelerating area. In that case, what happens? The area that is the accelerating area and the decelerating area. This is accelerating and decelerating area. If both are equal, then the system is stable. Ultimately, at the end, it is settling down to this value. This is the concept of the equal area criteria that we are applying to the power to judge the stability of the power system.